So when we looking at the exercises, since we know so many different methods to find the series convergence or divergence, then I don't think it's correct to tell if you need to use one method rather than the other. And that's why it's a good idea to, well, just do problems one way, the other way, and then decide which way you like to utilize. For example, here we have a geometric-like series. If ratio was 10/9, which is greater than 1, then it's a divergent series without n. But if you start multiplying this increasing terms by numbers 2, 3, 4, 5, you get it even bigger. So it's definitely going to be divergent result. But again, maybe you can use the ratio test and show it a little bit clearly. But the message is you don't need it here because you already learned enough material to describe divergence. And that's the message. These tests could be used pretty much in any section of this textbook from now on, and that's why I guess it'd be a good to realize it. How about if I look at number 10, what you think about divergence of series that I could treat as 4 I can take out, I don't need it here. So it's e to the power of negative n from 0 to infinity. Well, looks like I can utilize the nth root test because I have a term that is raised to the power of n. So why don't I see what is the nth root from the nth term is going to be? Is it less than 1 or small or greater? So if I extract the nth root from the nth term, I'm going to have to use e to the power of negative n or 1 over e to the power. So this will be e to the power of negative 1 or 1 over e. Well, that's definitely less than 1 because e is 2.718. So it's like around 1/3. So we have a convergence series. Remember the little fact that we had just looked at in the table above, that if your limit of the nth term, nth root from the nth term is less than 1, one is, Alex, where's your limit? Well, you can put the limit. It makes no difference here. But yes, you can put the limit, because if you had that limit with us all the time, then you will eventually take a limit of the number, and that's the same number. So it makes no difference whether you put limit in this particular case or if you don't. So again, problems could be done any way you like. And on the final exam, I will expect you to do problems just your own way and show work. And even if you mess up a little bit, I see if you were on the right track, so you'll get pretty much entire credit for that. So just like we had for the midterm. Final will be last week of, actually first week of May, right? First week of May on Tuesday, final. And we have about 4 weeks to go, right? And actually, if you subtract this class meeting and the review class meeting, so that'd be about 6 class meetings before final. So today I plan to cover one section from chapter 9 that deals with so-called power series. Yes, I'm skipping a few sections because this class used to be 5 units and now they cut it till 4, so they decided not to cover Taylor's polynomials. So I skip that. And well, they plan to actually cut calculus 1 also to 4 units. So not sure what they're going to throw away from it. Maybe some applicational sections as well. As you notice that I also had to skip some of the applicational sections because it looks like we cut it, the class till 4 units. The review, I'm going to do a review in 6 class meetings. Right now, I just telling you what sections I throw away. So last section from chapter 9 will be 9.8 because there are a few sections that I skip in chapter 9. So last section is 9.8, but we'll do plenty of review and we'll actually have this, the practice final sent to you right before the last class meeting, so we can spend the whole class meeting for the review. Right now, I'm not doing the review, I'm just telling what sections we are looking at. So last section of 9 that I cover is 9.8, and then we'll move next week to chapter 10. And in section 9.8, we also have series, but they are very, very different. So for example, here, if you look at part A that has a sign alternating series that looks like -1 to the power of n divided by n factorial, if I look at that series, well, there'd be nothing special about this. It'd be a convergence series because this series has nth term that approaches to 0. It's sign alternating series. But now they multiply it by x. That's something we did not have in the previous sections. So it becomes a function of variable x. In other words, in this description, there are infinitely many series, actually. So, for example, when x is equal to 1, you're going to end up with a series that looks like -1 power of n over n factorial. But when x is equal to 2, you're going to get a different series. It'd be -1 power of n multiplied by 2 divided by n factorial. When you say, Alex, this actually has x to the power of n in this example. Yes, so here is 1, and here will be 2 to the power of n. Well, 1 to the power of n is just number 1. And you can see that we have totally different pair of series when your variable x is different. And notice that x is any real number, which means we have lots of those different series. Even though it looks nice and compact, but because of power of x present, there are infinitely many series. And that's why the section called power series that has exercises that are way more general compared to what we had seen before, because those other exercises were not functions with variable letter x. So you say, Alex, you had variable letter n. Not really. They were infinite sums. And for every value of n, there was a term. So we knew what happened with every term. But here, every term is multiplied by some power of x. And x would be any real number. So there are lots of different series. And I guess that's the key part I wanted to show you today, because that's, I believe, the most important idea to understand in this section. And then everything be nice and straightforward, I guess. So here they're talking about those series as functions of various powers of x. And that's why they're called power series. X raised to some power, like polynomial type. Eventually, you will see instead of x, other functions that deal with x, such as sine, cosine, those called Fourier series, but they all analogously worked out to the power series. So I guess the best way is to take the actual exercise and work it out, because nowadays there is really not much of theory, but I'll just looking at the practical exercises. So what I can do is look at the power series and see when it's convergent for what values of variable x. So let me start with exercise number 5, and then we are going to continue. So let me share some word here. So in problem 5, here we have sine alternating series that starts at zeros and continues through infinity. So it's minus 1 power of n multiplied by x to the nth power over n plus 1. So I need to take a look at the convergence of this series. And turns out the standard way to do for convergence is the test from previous section that says, take the limit of n plus first term divided by the nth term. And when this limit is less than 1, then we have convergence series. In fact, it's absolutely convergent series. And absolute convergence is the strongest for sine alternating series. In fact, if sine does not alternate, if all sines are positives or negatives, all of them, then we also have analog of absolute convergence, because everything is positive. Or if everything is negative, we just factor minus out and still have everything with the same sign. So let us take a look at this type of a limit and see when it is less than 0. So I'm going to look at the n plus first term in absolute value without this negative 1. So we got x to the power of n plus 1, right? Divided by, instead of n, I put n plus 1. And here's another 1. So this be x to the power of n multiplied by another x, and denominator is n plus 2. Therefore, my limit here will look like a fraction that we have for the nth term, which is multiplied by the reciprocal of actual nth term in here. So I'm going to take this x to the power of n. Notice I always want to separate it because eventually it's going to be canceled. It's always the same thing in all of these exercises. So now I flip that nth term, put x to the power of n on the bottom and denominator on the top. Why? Well, because I divide by it, right? I can write another line to verify it. So the nth term cancels, and this is great. So I find what the limit is. I think it's n plus 2, right? Should be careful. So looks like x has nothing to do with n. Whatever x is, 1 or 2 or pi or a billion, it'd be the same thing throughout every single term of my series. So all I need is just to find the limit of n plus 1 over n plus 2, which is equal to number 1, right? When n approaches to infinity. So I ended up with x multiplied by 1, which is just x. I say, okay, so what? Well, now it's a key part. We need to see when this is less than 1. Please also notice this is absolute value that we're talking about. So we're going to get an inequality here to solve. So I should have actually had absolute value because x could also be negative, right? So we have absolute value of x is less than 1, or in between of -1 and +1, we have values of x in here. And that's why sometimes people say the radius of convergence is 1. Well, I guess it's not really that interesting for us if you look at the interval in between minus and +1. So the radius is the distance to the center. It's like diameter is here, so half of it is radius. So that's why we say radius is 1. Well, what we actually do care about is to check out the case when it's actually equal to 1, because at that particular value, we are undecided, because remember the test for this absolutely convergent series only tells us when it's convergent, when it's less than 1, or divergent, when it's greater than 1. But it has a question opened if it's equal to 1. So when x is equal to 1, in other words, when x is equal in absolute value to 1, which means that endpoints of this interval that are +1 or -1 need to be tested. So then I can make a conclusion on what values of x my series is convergent and where it's divergent. So far I know for sure that it diverges everywhere from -1 to the left and from +1 to the right, but the question is, what about those endpoints? So we need to finish up with this, and now I need to try +1 for x in my original series, of course, and see what's going to happen in that case. So if I now consider series when we replaced the x with 1, and also I need to consider another case when we replaced x with -1 in the same exact series, and see what's going to come out. So looks like for the second case, my -1 is going to disappear, right? Because when I multiply -1 to the power of n by another -1 to the power of n, I'm going to get -1 to the power of 2n. And when I square it, I get 1, so that power of 1 was always going to be 1. And that's why my series is going to be, remember the name of it? Starts with H. What? 1 over n. Harmonic, right? Harmonic series. So harmonic means convergent or divergent? Anybody remember? Harmonic. And this other series is going to be sign alternating, because that -1 really means nothing. That +1 to the power of n is actually 1. So that's a sign alternating. So the nth term of that series is going to be approaching to 0, right? Since it's sign alternating because of -1 to the power of n. And that's why we call this series as what? Convergent. So my series is convergent at point 1. And when we have the other end, we get harmonic or divergent series, which means that my extra fact is here. So that's when series converge from -1 not inclusively to +1 inclusively. And that's the key idea here. So since you have infinitely many series, the test gives you ability to get the result for a huge chunk of it, but the endpoints is what I always have to test. I say it's in every single exercise. Well, I guess, excuse me, there are always exclusions. I really don't feel well today. I have been vomiting all morning. Now looks like it's coming again. I got some kind of infection, I guess. So anyways, so it looks like we have the endpoints to test. Of course, if it's from minus to plus infinity, we cannot test infinities, but when it's finite, then we can test the endpoints. I think I'll do one more exercise and then I'll let you go because you deserve it, right? So let me just share another page in the textbook and select another problem. And looks like these exercises, they have a few steps in each of them. So you first of all test the interval, and then to find the interval, and then you test the endpoints. So what I want to do is find one that we can utilize instead of ratio test, the root test, because you don't have to always utilize the ratio. And maybe I can look at exercise number 25. How about that? Exercise number 25, because n's powers, n on the top and on the bottom. That's why I selected it. You could technically use the test that I just had in the previous exercise, but just to show you that you don't have to be stuck with the same exact problem. You could actually extract the nth root. One say, Alex, but that's n minus 1. Well, you can extract n minus first root. You see, how come I can extract n minus first root? Well, for example, if you replaced n minus 1 with a k, then n will be k plus 1. In other words, if your series here starts at 1 for n, then k will be, so if n is going to be 1, then k will be 1 minus 1, which is 0. So you just converted your limit. So I can have this series from 0 to infinity. So I can always manipulate those indices. I think this is interesting to realize, right? Just like you did substitutions when integrated. So now power is k, and then 3 to the power of k on the bottom. So technically, you didn't have to do that. You could just extract the n minus first root on both terms, because you extract an nth root. So who cares if that's n or n minus 1 or n plus a million, as long as it's the same root from the entire case term in here. So I'm looking at the limit of the nth root of that nth term, and this is going to be just extract case root, right? K or n, doesn't matter. So this will be a limit from, I'm not going to write this case, so just write it as a x minus 3 divided by 3. And notice it's an absolute value, so I put this absolute values. And this limit is actually the same thing because there is no n or k involved in here. So this limit will be this same absolute value. And now we compare it with number 1. So if it's less than 1, then series is convergent. That's what we had for the nth root test. So now I need to solve this inequality for absolutely convergent series. So I put in between of plus and minus 1 my expression inside the absolute values. And you say, why is that? Well, because when absolute value is less than 1, then the number has to be in between of plus or minus 1, because if it's outside, the absolute value will already be bigger than 1, or if it's a big negative number. And that's why my expression inside the absolute values must be in between of these two numbers, you see? So it looks like now I'm gonna triple both sides, actually all 3 sides of this inequality. So little by little we're solving this. So there's no denominator, right? So we're in between of minus 3 and plus 3. And then add in 3 everywhere, so nothing changes. Then we have x, which is in between of 0 and 6, right? And again, if you need the radius of convergence, take a half of this so-called diameter and be 3. But my goal is now to see what happens at those end points. So let me plug in the series and 0 and 6. So that's a standard ending for the exercises. So once you have those endpoints, we'll always replace x with those values and see what happens. I say, do you have to replace it in the original or with the one that substitute? It doesn't matter to put k plus 1 or minus 1 or k, still be the same series. Look at this. 0 minus 3 to the power of k. Looks like sign will alternate, right? Over 3 to the k. Alternating sign series. And here we have 6 minus 3 to the power of k divided by 3 to the power of k. Please notice that in the second series, everything is going to cancel, and that makes me happy. I just love to cancel. But what's going to left? Well, sum of ones. Like 1 plus 1 plus 1 plus 1, dot, dot, dot. It's divergent series. N's term is 1, not approaching to 0. Okay, how about the other one? Well, looks like this is going to be a -1 to the power of k that I can factor out. And exact same thing is going to happen with 3 to the k's. They're going to cancel. So this series will be a -1 plus 1, -1 plus 1. Looks like if it starts from 0, the first term will be -1 to the power 0, which is 1, then -1, 1, -1. This is also divergent series because, again, n's term is not approaching to 0. So our series is absolutely convergent on the open interval and between 0 and 6. So we got that answer. So as promised, I'm not going to give you a quiz today. I just want you to look at this and think about it because it's not obvious. This section already brings us to a little bit different area of math, even though it's serious, but it's a little bit different. So let me go to the contents since I promised to stop at this stage, and I will just tell you what be the plan till the end of semester. So we already had the chapter 8 for the test, but we stopped at the L'Hopital's rule. That's a very useful rule. So we had a cutoff here for the midterm. So for final, we'll start at 8.7, 8.8, and then chapter 9, a few sections. So it looks like we are to cover the power series, and then first 5 sections including alternating series. So don't do 6, 7, 9, and 10. And then we're gonna look at 10.1 and then 3 and 4. And if time allows, I also look at the 10.5. And it'd be awesome if I could take a look at the Taylor series and Maclaurin series. I think that's a very nice section. And that's why we'll see if it works out, because as I said, there are 6 class meetings left, and maybe I'll be able to do it because I think we have a good pace in this semester. That's why I think I could also take a look at that. So that'd be the plan till May, and I'll let you go and enjoy the weekend and have a good weekend. I guess they say it's Easter time, so enjoy the holiday, and we'll continue on Tuesday. On Tuesday, we're gonna look more at 9.8, so maybe you'll bring up some questions that I can help you with. That'd be great. So no quiz today. I'm gonna stop and let you enjoy the weekend and the holiday, and we'll continue, of course. Have a good night. Bye-bye.